is the normal force acting on the person in these three locations. They're not moving, they have a gravitational force. The force of gravity is downwards, and you use mg, the mass times the acceleration of gravity, to calculate that. So we designate that mg, and then we want to figure out what the normal force is. The normal force pushes up because the person's not falling through the floor, and therefore we're going to designate that as Fn. The force of gravity pulls down. You have gravity, you're near Earth, we call that mg. Well, you're not falling through the floor, so excuse me, the seat there, so therefore there's a normal force, and we're going to call that Fn again. All right, now we did say that you're accelerating because you're going around in a circle. Even though you're standing, it looks like you're standing still in this picture, you are going around a circle. So you are accelerating, you're constantly moving around a circle. And we said that the acceleration is towards the center. So I'm going to draw the acceleration vector like this. It doesn't point towards the center, but if I was to put it over the person, it would point towards the center. And it points downwards, and we call that the acceleration. Now, the last thing we have to do is we have to designate the positive direction for this case. And the easiest thing to do, and the most common thing that is done, is you say that the direction of the acceleration is the positive directions. So we'll put mg first, so we have a nice positive one in the front, keeps the negative signs in the center here, makes sure we don't lose our negative sign, and then Fn points up. Up is the negative direction, and that is going to be equal to ma. It's a positive a, so we put positive acceleration, just put down ma, and therefore we know that normal force, in the case when you're at the top, is going to be your mass times g, the acceleration due to gravity, minus the acceleration of the roller coaster. So you can see if we calculate Fn, we're going to get a value that's less than our true weight. So if we had a scale and we brought it on the Ferris wheel and we sat on the scale, it would read less than our weight when we're here at the top of the Ferris wheel by a factor of minus a. Okay? Try the same thing for the bottom. So here we have the bottom. And we're going to do the same thing. We're going to draw all the forces in, be consistent here. The positive Fn. Fn points in the positive direction. Put that first. Mg points in the negative direction. So we put negative mg, and then once again our acceleration is up, but we said up is positive, so we're going to call that ma. So our apparent weight is going to be greater. Here we have our true weight. When we're at the top, if we're sitting on the scale would be less than our true weight, and we're at the bottom, we have another apparent weight, and it's going to be reading greater than our true weight.
For any planet, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun.
Applied to Earth satellites, Kepler's third law explains that the farther a satellite is from the Earth, the longer it will take to complete an orbit, the greater the distance it will travel to complete an orbit, and the slower its average speed will be.
Okay, now we can replace our A with 2 times RS. We're just going to plug this guy right into here. So we do that. Let's use green pen. So then we're going to replace RA with 2RS, but we'll still cube that over TA. Oops, this should be a squared. This should be a squared. This should be a squared. Equals R s cubed over ts squared. So with a little bit of work, we get this. Note we have cubed the 2 to make it an 8, and everything else stays as is. So if we look at this guy now, we see we have a cubed rs and a cubed rs. We can cancel those out. So this just becomes, we can solve that by just rooting both sides. So we can just root this side and root this side. That'll give us the square root of 8 times ts equals ta.
Hello, I'm Jeff Williams on board the International Space Station, an Expedition 22. Well, here in space and weightlessness, I have this bag of tea, and you can see it has bubbles in it, but they don't rise to the top. In fact, I'll shake them up here, and you can see the bubbles spread out throughout the tea. Of course, we're in weightlessness. We have the absence of gravity, and we know that bubbles rise for what reason? In the presence of gravity, the air is lighter than the liquid, so the air floats to the top. Gravity causes the liquid to go down, and that actually pushes the bubbles up. There's the bubbles spread throughout the tea, and if I rotate it, the bubbles coalesce to the center of the tea and eventually form a circle. Why do they do that? Because of the centripetal force spread throughout the tea. The liquid tea goes to the outside of the bags, and it forces the air into the center because the air has less mass, less density than the liquid. So the air goes to the center. I'll try it one more time. See the air coalesce to the center, form a circle. Due to the centripetal force applied in this, because it's turning, it's rotating, the liquid goes to the ends and the air ends up in the center of the liquid. Okay, that's enough. I'm going to just pull away from there. And what happened? There we go. And I'm going to take my piece of dental floss. And I'm going to just use the dental floss to kind of guide the water bubble. So let's see here. What I'm going to do is I want to try to rotate the water bubble. And we'll see what happens. Actually, I'm going to turn like this. I'm going to try to rotate the water bubble this way. Because if I give you this angle, you'll be able to see it change shape. Actually break into several parts. And you can see they're no longer cylinders. This one's rotating like this. And that's due to the centripetal force within the water bubble.